Hello, friends. Welcome to Science Talk. I am your host and resident oceanographer, Jim Massa. Okay, let's look at this here. Non-monotonic change of the Arctic Ocean freshwater storage capability in a warming climate. Now, before we go any further, we need to define what is meant by monotonic and therefore non-monotonic. Okay, that's basically a reference to mathematical functions. So if I have a mathematical function, and let's say f of x, y equals f of x, and I have x equals a and x equals b, and a is a value less than b. Okay? So if I take whatever that value is and I put it into the function f of a, and let's say I take the value of b and I put it in the function f of b, I get results. Let's say that no matter which a and b I choose, if a is always less than b, and f of a is always less than f of b, then we say the function is always continually increasing. That is, it's monotonic. All it does is increase. Conversely, a is less than b. That's usually the standard we take. But if f of a is greater than f of b, no matter where I go along the function, then the function is said to be continually decreasing. Still monotonic. So basically, a monotonic function is where on every interval, it's always increasing or always decreasing. If there are intervals where the function increases, then decreases, and increases again, whatever, it's non-monotonic. So what would be an example of a non-monotonic function? A parabola. If the parabola, is one that opens upward, so that the vertex is a minimum, to the left of the vertex, the function is decreasing. To the right, it's increasing. But it changes from decreasing to increasing. Non-monotonic. A good example of a monotonic function is a straight line. Going up or going down. Straight line. So basically what the saying non-monotonic change of the Arctic Ocean freshwater storage is that it's always changing. Okay, so hopefully now that you have an understanding of what's meant by non-monotonic change and function, let's take a look at the abstract here. What they have here is that freshwater in the Arctic Ocean is one of the key climate components. It is not well understood how the capability of the Arctic Ocean to store fresh water will develop when freshwater supplies increase in a warming climate. By using numerical experiments, we find that this capability varies with the Arctic sea ice decline non-monotonically, with the largest capability at intermediate strength of sea ice decline. Through enhancing the ocean surface stress, sea ice decline not only accumulates fresh water toward the Amerasian basin, but also tends to reduce the amount of fresh water in both the Eurasian and Amerasian basins by increasing the occupation of Atlantic origin water in the upper ocean. An increase in river runoff modulates the counterbalance of the two competing effects, leading to the non-monotonic changes of the Arctic freshwater storage capability in a warming climate. Okay, so that's their abstract. And you're probably going to say, what are they talking about? And this is we see here plain language summary. This is kind of a recent development in the last couple of years, because basically, when I was doing this stuff here, we were just communicating to our colleagues. So, we use all this dry language, dry reading stuff, and kind of wonky. But hey, we understood what our colleagues were saying. But there's a move, and I welcome this move among scientists to try and make our research more accessible to the general public, more easily understood, so that they get a handle or understand what it is that we do and the significance of the work that we do. So now we see things like this. Plain language summary. Okay, here we go. The Arctic Ocean is a giant freshwater pool of the Earth's system. In a warming climate, the Arctic liquid freshwater content is expected to increase because more freshwater tends to be, I like this word, hosed into the Arctic Ocean. Now, by the way, throughout this paper, when they talk about freshwater content, it's abbreviated as FWC. So keep that in mind. Will the Arctic freshwater storage capability change? In this work, we conducted numerical experiments to show that sea ice is a key controller of the Arctic freshwater storage capability. With the shrinking sea ice, more freshwater is transported from the Eurasian basin to the Amerasian basin. In the paper, this is abbreviated EB, AB, respectively. In the meanwhile, more saline water fills up the Eurasian basin and further propagates to the Amerasian basin as well. The opposite effects of these two processes cause a first increasing and then decreasing change in the Arctic freshwater content following the strengthening of the sea ice decline. However, the increase of river runoff can delay the transition between the two phases, leading to a bell-shaped Arctic freshwater storage capability. The maximum capability occurs at a moderate strength of sea ice loss. Our studies suggest that the impact of sea ice decline should be adequately considered when predicting changes in Arctic Ocean environment and its changing role in the climate. Okay, so what are they talking about here? When the ocean freezes to form the sea ice, okay, what happens is, in forming the ice, you leave the salt behind in a process called brine rejection. That will increase the salinity of the surface waters, making it more dense, so we start getting a little bit of vertical sinking. Okay, fine. Now, later on in this paper, they're going to be talking about various schemes and what does it mean for stratification, Ekman pumping, downwelling, and transport, Ekman, advection, all sorts of stuff. Basically, if you've got more saline water at the surface, which would be more dense, it's going to sink. You're going to not see such a strong gradient in the salinity. You're still going to get a halocline and so on, but you're not going to see that strong a gradient. Well, now when the sea ice now starts melting spring, summertime, this water now is diluting the surface. So the salinity is reduced. The density is reduced. So any sinking, vertical sinking, is going to be reduced. This will lead to a more pronounced stratification. Add to this all the freshwater input from rivers, such as the Mackenzie, the Lena, the Ob, etc. How does this affect the situation? Okay? Now, I did a couple of shorter videos talking about the freshwater content in the Arctic Ocean, how it's how it moves through the Canadian archipelago, and so on. So here is a case where this is a detailed paper looking at this situation here. Now, of course, I will leave in the comments the URL so that those of you who are interested can click on the URL and read the paper in detail at your convenience. So that's what's going on here. Now, when they talk about water, saline water fills up the Eurasian basin, they're basically talking about the intrusion of North Atlantic water. It's warmer, but is much has a much higher salinity, so it actually becomes dense. As I showed you in the sea ice melt video that I recently did, this North Atlantic water actually slides under the halocline. Well, as it's sliding underneath there, it's going to help do what we call ventilate any sections of the ocean. Usually ventilate down to the substrate, so down through the basin. That does not seem to be some of the processes involved in the Arctic Ocean, because when you get into the deep basins, especially the Amerasian Basin, those waters tend not to be ventilated. So that North Atlantic water tends to be more of an intermediate water into mid-depths that they're found in the Arctic Ocean. But still, it is playing a role in what's going on here. So basically what they're trying to figure out here is, if the fresh water pools up, the fresh water being the source from the sea ice, riverine input, if the fresh water pools up, you're going to get marked stratification, and therefore the vertical mixing, vertical sinking is going to be inhibited. And if that's the case, you get the strong stratification, that's going to pose problems for primary and later productivities. I've discussed with you before how when the ice melts, you get ice edge productivity, but don't forget you have algae on the underside of the ice also doing productivity. We're losing the sea ice, so we're losing those two sources of productivity. I also discussed with you that just because you don't have sea ice, the phytoplankton cannot really start doing a thing until the sun is at a sufficiently high enough angle in the sky to activate the electron transport chain system, part of the photosynthetic process. But if we now have this stratification under the pooling of the freshwater scenario getting stronger, this could very well inhibit any nutrients from below the pycnocline, the halocline, from being infused into the upper waters, thereby drastically reducing primary productivity. So there's that scenario. The other scenario they're looking at is, well, does the fresh water, due to various advections and other mixing forces, we have the Arctic boundary current, as I showed you in the Arctic sea ice melt video. We have that, so that can move water around. There's the Beaufort gyre, which, by the way, is abbreviated BG in this paper. There's the Beaufort gyre, which has a convergence zone in the middle with subsequent downwelling. That's the Ekman pumping. So if you have that, if you are able to somehow remove the surface fresh water, then you get the scenario where you don't have a sharp gradient in the salinity, and therefore the stratification may not be as strong. And you might be able to get some mixing, especially during winter months when there tends to be a breakdown of such things. So those are kind of the two scenarios that they're going to be wrestling with in this study, and they discuss it later on. So that's kind of the abstract there. And let's get into the introduction here. Significant increase of liquid freshwater content, is the FWC, in the Arctic Ocean has been observed since the mid-1990s. And they list a bunch of references here. This freshman trend can dramatically impact the biogeochemical processes, such as I kind of just briefly outlined, in the Arctic Ocean. A fresher halocline, that means lower salinity, and halocline is a drastic change in the salinity, also renders a stronger barrier between the floating sea ice and the warm Atlantic water at depth. That's kind of what I was just trying to describe here. You have the infusion of the North Atlantic water underneath basically extremely reduced salinities. And I just want to mention Polyakov. It's Igor. He's a good friend of mine. Worked with him. He's a wonderful gentleman. He does excellent work. So if exported to the Atlantic Ocean, the fresh water could significantly impact the large-scale ocean circulation and climate by suppressing deep water formation in the North Atlantic. So, in the second scenario outlined, due to various advection, currents, and what they refer to in this paper as ocean stress, the fresh water could then be, instead of remaining within the Arctic Ocean basin or at the surface, it could be moved out the Arctic Ocean, typically through the Fram Strait, in which case you remove the fresh water, but you're now putting it into the North Atlantic. This is in addition to the melting from Greenland. And now you have two potential sources of freshwater input into the North Atlantic. Of course, if you put the fresh water there, as I've discussed with you many times before, you then inhibit this vertical sinking, which is the start of the thermohaline circulation, and which is the start of the conveyor belt. So the freshwater input in the surface of the North Atlantic reduces the salinity, reduces the density. It doesn't sink. So you pick your poison. Do you want to keep the fresh water in the Arctic Ocean, or does it get moved into the North Atlantic? So that's what they're talking about here, which is very important. Winds associated with different atmospheric circulation regimes can drive changes in the Arctic freshwater storage. For example, an anticyclonic wind regime functions to increase Arctic freshwater content through Ekman convergence and the subsequent downwelling. Okay, translation. The Beaufort gyre is what they're referring to here. Now, anticyclonic is basically a clockwise rotation in the northern hemisphere. So you have the wind stress that pushes on the water, and then pushes on the water. You have a deflection, generally taken to the right when you integrate over the water column. That causes a piling up of the surface waters in the middle of the gyre, doming up. So it's a convergence zone, and then you have a subsequent downwelling. That downwelling is, the Ekman convergence, Ekman pumping. And by the way, there's a principle called conservation of volume. If you're putting water in, if you're moving water into somewhere, you have to remove water. Just like if you pull water out, it has to be replenished. Now, in the cases where you start melting the big glacial sheets, well, now you're just adding a whole bunch, and guess what? Sea levels go up. So that's what they're talking about there. The response of the Arctic freshwater content to winds, however, can be partially counteracted by eddy fluxes, basically changes in surface flows, little gyres that pinch off the main flow, that kind of situation. Sea ice is an important mediator of the freshwater content, spatial distribution through its impact on ocean surface stress. Okay, I want to go back where they're talking about winds associated. When the wind blows across the water, that's imparting a stress called wind stress. Okay? And so you the wind pushes, air pushes on the water is then moving, and the water is now pushing on the layers of water underneath it. So that's another stress. And then that layer pushes on the layer beneath that, and so on. What we generally find is that the greatest magnitude is at the surface, and the magnitudes decrease as you go deeper. But thanks to Coriolis, with the deflection, as you go down in depth, it keeps deflecting to the right, you create what's called the Ekman spiral. And then when you integrate over that column, the mass transport is to the right of the original wind direction. Coriolis is dependent on latitude. The higher the latitude, the more pronounced is the effect. It's basically taking the sine of the latitude. It goes from 0 to 90, and then 0 to minus 90. So at the equator, there is no Coriolis effect, no deflection. The sine of 0 is 0. But at the North Pole, and guess what? That's where the Arctic Ocean is. Okay? The sine of 90 is 1, so the Coriolis is most pronounced at higher latitudes at the North Pole. And we see that here with the Beaufort gyre being a very tight gyre. So that's what they're talking about there. Freshwater sources for the Arctic Ocean, including continental runoff discharge. Those are the rivers I mentioned earlier. A little bit through the Bering Strait, and then net precipitation minus evaporation. And of course, the aforementioned melting of the sea ice. Basically, you tend to have more precipitation that's been going on lately than evaporation, so that is adding fresh water. And all of these factors have been increasing over the past few decades. And there's Dr. Woodgate, Rebecca Woodgate. I shared some of her work with you in the sea ice melt video. These changes might be the signals of climate change. Well, in science, we always write with caveats. That's basic, that's just what we do. We never say, oh, we can say with 100% certainty. We say with 95% confident, 99% confidence. That's kind of what they're doing here. An even stronger increase in Arctic freshwater sources in future warming climate is expected. With an increase in freshwater supplies, the Arctic freshwater content will increase even without changes in winds above the Arctic Ocean. Although not all excess freshwater will be, I think they meant to say, held in the Arctic. While these studies document the response of Arctic freshwater to increased freshwater sources, it is still not known whether and to what extent the response is influenced by contemporary changes in the Arctic sea ice state in a warming world. So basically, they now state that they're going to test the hypothesis that the increase of the Arctic liquid freshwater content in case of enhanced freshwater supplies can be significantly influenced by the Arctic sea ice state. That is, by sea ice decline induced by the climate change. Sea ice is declining, that's adding freshwater content. They're saying that this might help increase the freshwater content in the Arctic Ocean. Again, go back to those two general scenarios I outlined just a few moments ago. We'll investigate how the freshwater storage capability of the Arctic Ocean will develop in a changing climate. And then they go on to say, we'll explore this, explain what we're doing and the methods. Okay, I'm not going to go, again, you can pull up the URL and read the details of the methodology. What I will say is this. Let's look at this. So they worked with 6 models here. And they have historical. So I have a couple of historical models here. And then they have these different situations. So what the models are based on the surface air temperature. Surface air temperature is typically taken at 2-meter heights above the surface. And so they have the temperatures in degrees C going from 0 to minus 14. Historical, that's basically from 1970 to 1989. And then another more recent kind of baseline from 2000 to 2009. And then the 4 different scenarios based on what the anticipated warming of the Arctic air is going to be. So in other words, from say 13 or so, maybe to, what that looks like 8, or to 6, 4, and 2. Well, that's that 1. That looks like 1. So they run these different air temperatures, and under these scenarios, basically what they did here is, and I'm going to increase this a little bit. There we go. They looked at what these different models, what will be the resulting sea ice concentration. So when you get into the red, I guess that's brown, whatever, that's 100%, so very thick sea ice. Down to 0, that's open water. Okay? And so here's the historical. As you can see, a lot of ice. Ice is not as much. And then, so these two are actually based on data. And this is based on the data here, they did some modeling projections. And as you can see, this refers to the temperature of basically 8 C, and then, 6, 4, and 1, etc. So when you get to the 370 which is this one here, which is 3C. So the air temperature is warm from basically 13 to 3C, so that's 10 degrees Celsius. When you get to that, it's, except for a little bit right there, it's basically open water. And of course, when you get to here, totally open water under that. So this is basically blue ocean events. This black line is the Lomonosov Ridge separating the Amerasian from the Eurasian basins. And so they explain, the annual mean surface air temperatures averaged over the Arctic Ocean in the 6 forcing scenarios. And they take it from there. So the blue star is the left side of the section. So when we look, so that's basically the Mackenzie River. So when we look at some of the later diagrams, the blue star is basically the starting point. So that's what's going on. So these are the 6 different models, scenarios that they're doing. And then they use a different thermal forcing to carry out the simulations. They do a little explanation of some of the math here. So this is a straightforward integration. Freshwater content, you integrate from depth to the surface. 0 is the surface. And then S means salinity. So S is ocean salinity. And then with the subscript REF, that's the reference salinity set at 34.8. PSU simply means practical salinity units. Okay, and then divided by by this, and then DZ. Z is the variable we use for vertical direction. So we're integrating with respect to Z, the vertical direction, and then they go through a whole bunch of other stuff to calculate freshwater content. That's fine and dandy, but that's not the focus of what I want to share with you. Again, click on the URL. If you're interested, you can examine that. So looking at basically, these are all calculating freshwater capability. What that means is the capability of the Arctic Ocean to hold water, and therefore it hold fresh water. Okay? If the freshwater storage capability is larger than 1 in a certain climate scenario, it indicates that the Arctic Ocean in this scenario is able to store more fresh water than in this historical 70 to 89 period, even when river discharge has the same increase. In a particular case for the 70-89 time period, capability is equal to 1 because the denominator and numerator are the same in a fraction. They use the same analysis in the cases of tripling the runoff, and so on. So basically, as we'll see later on, they have river runoff, based on current levels, that's 1x. And then they say, well, maybe the river runoff will increase because of melting snow, maybe melting alpine glacier. So will it double? Will it triple? So they examine that. Okay, so now looking at the results here. Let's start right here. It says the Arctic summer sea ice coverage is lower under warmer thermal forcings. That is not a surprise. The Arctic Ocean is already close to be sea ice free in summer when we're looking at the 370 scenario, which I showed you earlier. Basically, that's their way of saying a blue ocean event. Reduction in sea ice concentration and thickness with increasing climate warming occurs, this is critical, all seasons. That's very important. The changing Arctic thermal forcing exerts important impact on the Arctic freshwater content. It increases at first, then decreases with the strengthening of atmospheric warming, and this happens in all 3 cases of river runoff forcing, 1 times current amount, 2 times, and 3 times. The freshwater content in the Amerasian Basin also has a maximum at intermediate levels of climate warming. And it's saying, look at figure 2b, which is this right here. I'll go through that in a moment. In the Eurasian Basin, the freshwater content decreases with increasing warming, although the changes between the first 2 historical scenarios relatively small. And then they go on to say, it's interesting to note that while the Eurasian Basin freshwater content is much less than the Amerasian Basin, freshwater content, its change due to atmospheric warming is as significant as that of the ABFWC. Increasing Arctic River runoff results in an increase in Arctic liquid freshwater content in both of the basins. So what they're basically saying here, and I should just plain said it, is this whole business of, it decreases with the strengthening of the atmospheric warming, basically saying that it's starting to evaporate some of the surface water, thereby reducing the freshwater content that is found. Initially, when it's not as warm, it can accumulate, and that's this increase at first. So to me, that's basically indicating evaporation taking place. So let's take a look at this figure here, and this is the freshwater content, and it's 1,000 cubic kilometers, okay? And this is the Arctic freshwater content as a whole, the Amerasian Basin, the Eurasian Basin. And this is what they were talking about. We see the increase at first, and again, referring to each of the different models. We see the increase at first for 1 time, 2 times, 3 times the runoff. And then it levels off, declines a bit in the Amerasian Basin, where the Eurasian Basin is constantly declining. Then they look at the freshwater increase, again, in thousands of cubic kilometers. And we see basically this kind of the same pattern, except a little bit of an increase here and then a decrease here. So what do they have here? So D2F, that's this middle row here, the freshwater increment in the 2 high river runoff cases reference. So here we looked at all 3, and then they run the model for just looking at the 2 times and 3 times the river runoff here. And as to be expected, you're going to have increased fresh water because you increase in river runoff, and there's a decline. This decline is probably due to the evaporation. Now, the last row here, okay, is freshwater storage capability given as a percent. Okay? The freshwater storage capability is defined as the ratio between the freshwater increment in different climate scenarios compared to the historical 1970 to 1989 time period. Okay, as to be expected, if you're comparing it to 1970 89 historical time period, you would expect to see a value of 100%. So what are we seeing here? We're seeing that overall for the whole Arctic Ocean capability, that the storage of fresh water has increased. So if I look at this value here for the 245 model scenario, that's calculated to be 120%. That means it's 20% more than what was historically for that time period, 70 to 89. That's what that means. Same thing over here if we look at the Amerasian Basin. Now, for model 245, it's 140, so it's 40% more. And then for the Eurasian Basin, about 30% more. This is similar to the AGGI, the annual greenhouse global index, where you calculate the ratio compared to the 1990 ratio. Basically, you're looking at the total forcing for whatever year of interest divided by the total forcing for 1990, and that gives you a value. So if you got a value, say 1.27, that means there's 27% more heat forcing, watts per square meter. Well, this is basically saying that when compared to this is the baseline, basically. Keep that in mind. 70, 89 is the baseline. When compared to that, we see the storage capability has increased, and you basically do the difference. 120 minus 100, that's 20% difference. Okay, if I look at this one here, the red for 2 times the runoff for model 370, that's also 120, also 20% increase. Look at 3 times the runoff for model 585, and we're looking at about 30% more increase. So basically what this is telling us is that the freshwater capability is increasing, meaning there's more of it. Now, what is interesting is to see this value here for both the 2 times and 3 times runoff of model 585. You will note it's at 95%. So that means there has been a decrease in freshwater storage capability of 5%. That's very interesting. And I'll explain why that is in a moment, along with these, which will then tie into why these guys are decreasing. So that's basically the information being conveyed here in this figure. Now they talk about atmospheric thermal forcing can affect the freshwater content spatial distribution. That's this figure here. Okay. The amount of fresh water keeps decreasing in the Eurasian basin with increasing atmospheric warming, while it increases first and then decreases in the Amerasian basin. The latter decrease occurs because saltier Eurasian water advects to the Amerasian basin, as manifested by the extension of the negative freshwater content anomaly from the EB toward the Canada basin. Okay, which ties into that very last thing I just showed you in figure 2. So what is going on in figure 3? Well, let's take a look. Okay. Again, this is the historical time period. Now, keep in mind, they're showing these values in meters. Okay. What this is not saying, oh, this is 25 meters higher than, say, over here. No, this is a cumulative measure. These are cumulative measures. The black line here that you see in all the panels, that's the Lomonosov Ridge, separating the Eurasian from the Amerasian basin. Right? So what basically is showing is that under the different models, you're losing fresh water in the Eurasian basin and you're gaining it in the Amerasian basin. Part of that is evaporation, but a lot of it is advection. You have the Arctic boundary current that runs along the edge of where the shelf starts to go down to the deeper depths. So you have advection, moving the water around, and then you have the Beaufort gyre right here where there's going to be some Ekman pumping that can move some of the fresher water around. And some of the surface advection will continue this way through the archipelago and out the Fram Strait as a possible scenario. As see here in the caption, liquid freshwater increases in the Amerasian basin, decreases in the Eurasian basin when sea ice keeps declining from the coldest to the warmest scenario. With the progress of the sea ice decline, the negative anomaly penetrates to the Amerasian basin also. Only the runs with 1 times the runoff, basically showing, current riverine runoff right now. The 2 and 3 times is done in an appendix. So this is basically what it's showing. This is showing a cumulative decline over the time period that the models will run of water. So this is showing freshwater loss from the Eurasian side, freshwater gain on the Amerasian side due to, as they explain later, various physical processes moving the water around. The response to the Arctic freshwater content's spatial distribution to atmospheric warming can be explained by the impact of sea ice on ocean surface stress. As suggested in prior studies, changes in sea ice coverage and internal stress, latter function of sea ice concentration and thickness, can significantly influence the ocean surface stress. Okay, what is meant by ocean surface stress? There's a couple of stresses here involved. And stress is just simply a physicist's way of saying imparting a force. So I have a wind that blows across the water. The wind interacts with the water. Friction imparts a forcing. It's going to move the water. That's a stress. You're stressing the water. You're imparting a force. Now, so the wind's pushing on the surface water. That's imparting a stress. So that water's moving. But then that surface water is also going to be influencing the layers underneath that. So it's in turn will put a stress on the layer below that. So that moves. And then that second layer will impart a stress to the layer yet underneath that, a third layer, and that will move. And so on down the water column. Then when you figure in Coriolis, which, by the way, increases as a function of latitude. So Coriolis is defined as 2 omega sine phi, where sine phi refers to, you take the sine value of the latitude. At the equator, there is no Coriolis because the equator is 0 degrees. The sine of 0 is 0. North Pole is 90 degrees, or pi over 2. The sine of pi over 2 is 1. So the Coriolis is most pronounced at the North Pole. And we are in the Arctic Ocean, so we're going to see a more pronounced Coriolis. So the wind's pushing on the water, it's going to deflect to the right, and that column, the layer underneath that initial surface is going to push to the right, and the one below that to the right, and so on, so that when you go down the column, you basically create what's called an Ekman spiral. Integrate over the column, you get net mass transport, which is at 90 degrees to the right of the direction of the wind and pressure gradient, all sorts of things going on. Lots of physics there. I explain all this in detail in my rotating systems video. Check that out. But what's going on here is basically, so that's what stress is. When you have ice, okay, the wind can blow on the ice, okay, ice absorbs a lot of that buffering. There is going to be some movement of the ice on the water that it sits on, so that is also another stress. Now, the type of ice will determine the kind of stress. If you have a big solid sheet of sea ice there, not a lot of stress is going to be imparted to the water below. But if you have something like frazzle ice, greasy ice, pancake ice, where the ice isn't very thick, where there's a lot of spaces in between the ice, then the stress is going to be more than just a big solid sheet as well. So the stress is basically the pushing, the result of a force being applied. That's what it stresses. When we say stress, it's an applied force. Wind pushing on the water, water pushing on water, ice pushing on water. So that's what they're getting at there. And they go on to talk about the change in ocean surface stress is considered enhancement because the stress anomalies are largely along the direction of climatological ocean surface stress. Two major features: anomalies directed from the Eurasian coast to north of the Greenland, and the anticyclonic anomalies in the Beaufort-Gyra region. The corresponding Ekman transport anomalies are directed from the Eurasian to the Amerasian basin with a convergence towards the Beaufort-Gyra, and that's going to be shown in this figure when I will enlarge that momentarily. This is a very important figure because, especially on the right column graphics, as we'll get to in a moment. So they go on to say that the stronger the Arctic sea ice declines, the larger are the ocean surface stress and Ekman transport anomaly. Makes sense. More open water, more wind stress. Changes in atmospheric circulation regimes are able to change the upper ocean circulation, shifting the front between Eurasian and Canadian waters. So let's take a look at this very important graphic. These all dealing with stress. And now here the red line is that Lomonosov Ridge. I'm going to explain what this is in a moment. This is very important. This is very... So the top panel is looking at Ekman transport, okay, for the historical baseline, and then for two of the warming models, ones with the most warm. When you look at these graphics here, okay, the arrows tells you the direction, the shading tells you the magnitude. And if you look at these arrows here, okay, we see something of a clockwise anticyclonic motion. Here is your Beaufort-Gyra right here. We see that here as well, Beaufort-Gyra. Now take a look as things warm up, and we can still see a little bit of that flow, but now take a look, see how it's a general clockwise motion almost across the whole Arctic Ocean, except for here, where now we start seeing some import here. Here's probably some of the riverine introduction. That's the word I'm looking for. Introduction, almost forming this little bit of a ridge here. As we add in more fresh water, look how everything changes. This is the convergence, the transport from the Eurasian side to the Amerasian side, dumping it into here, creating basically a downwelling right there. The water's going to be doming up here. We still see a little bit of that clockwise motion, but now we're starting to really push, put this fresh water introduction into the moving from one side to the other side. That's what this is showing. And we can see more of that here. But this is clearly showing the movement of the fresh water over from one side to the other. And this is the forcing. So it's in newtons per square meter for the top row. And then this will be newtons per square meter. So basically 10 to the minus 2 or 10 to the minus 3. So it's an order of magnitude difference. And so that's the forcing. And this is, how many square meters per second. So this is the velocity. That's what this is showing the forcing and the velocity. So this is demonstrating the movement of fresh water from one side to the other side in the Arctic Ocean. Now, let's look at this here. G is the vertical salinity transect. Now, you might remember from an earlier figure I showed you, there was a blue star there, basically like in the Mackenzie River Delta. That's where the transect starts at. So we go, 1,000, 2,000, 3,000, whatever kilometers from that reference location. When you look here, the purple and blue lines in the right panel, purple, blue line, are the 30.5 and the 34.8 practical salinity unit isohaline. Vertical black line indicates the North Pole. Okay? So, what do we see looking at the transect? I'll get to H and I in a moment. When we look down the column here, the deep purple has a PSU, practical salinity is about 29. Then as you get to the green and the pale green and flesh color it gets more saline. So when you look at this here, you can clearly see the influence of fresh water right here. And of course, it makes sense as you go deeper and deeper, the salinity increases, and also the density will increase. They talk about how the effect of the fresh water being dumped into the Eurasian basin, and if it gets Ekman pumping, can take it down to about 300 meters. Well, here you see it. There's your signal. And then when you get below that, it's almost uniform salinity. So now you see it seems to be the isohaline seems to be moving vertically towards the surface. What's that all about? Well, let's take a look at these guys here. Okay. These are, if you look at the chart below, these are the differences in the practical salinity unit. So 0 means no difference. To the red means it's higher. To the which would be positive, and to the blue, the purple, be negative. So it's a lower PSU. Again, these are those two respective isohalines of 30.5 and 34.8. And what this shows is this is showing that it's much fresher water. That's the Ekman. That's advection, Ekman pumping, moving the fresh water around. It shows it right there under the two different scenarios, but we get similar results. So what's going on here? Why is this more saline? What's the split here? What you're looking at here is the North Atlantic water intrusion. This is a clear signal of the North Atlantic water influencing from the surface to intermediate depths what's going on. So when we take into account that we're moving the fresh water from this side to that side, well, makes sense. The salinity has increased by about 0.8 practical salinity units, and this has decreased by a corresponding 0.8 practical salinity unit. So this is showing clearly the movement of fresh water, as I showed you here over here, from one side to the other. But then if you move the water here, you have conservation of volume. It has to be replenished. And this is being replenished by North Atlantic water that is, even though it's warmer, it's saltier. So it's moving in. That's what this shows. And that's why these isohalines are moving up here. This is the North Atlantic water moving in. Very astonishing result. Very important result. This goes to what we've been referring to as the Atlantification of various parts of the Arctic Ocean, the intrusion of Atlantic water into the Arctic Ocean. That's what this clearly shown. Remember, SSP 585 and 245 are just different warming scenarios depending on how much warmer the air temperature is. And so, similar results. That clearly shows what's going on. North Atlantic water moving in. Very astonishing result and very important. So that's what's being explained there. The ocean's salinity changes response to surface Ekman transport, described above, as I just showed you. And then they go through a whole bunch of explanations here. One hand, freshwater surface is accumulated toward the Canada Basin. On the other hand, the Eurasian Basin becomes more saline. When it's up, freshwater in the upper ocean shifts to the Amerasian Basin, increasingly filled by saline waters of the Atlantic origin. I just showed you that. In the Amerasian Basin, the freshening happens mainly in the upper 300 meters. I just showed you that. In the EB, the saline tendency of the upper ocean is associated with a clear uplift of the 34.8 PSU isohaline. That's this right there, as we can see in those three panels. So I showed you all of that. Due to a limited amount of surface freshwater to supply from the EB to the AB, saline anomalies can even extend into the AB with enhanced sea ice decline. This explains why the liquid freshwater content in the AB increases first, then decreases as sea ice continues to decline. They then talk about the historical runoff and looking at that, and they go through a whole bunch of explanations, interpretations, etc. I'm going to put the URL. So if you're interested, just click on the URL and you can read this and take your time to digest what they're saying here. Freshwater storage capability is calculated for the whole Arctic Ocean for the two basins. And when I went through that, in both basins, the maxima in the case of stronger river runoff forcing are located at stronger warming scenarios. Integrated over the whole Arctic Ocean, the maximal freshwater storage capability is still as high as 120%, those 20% above the historical levels. With both river runoff forcing, this value is lower than those in both the AB and EB because freshwater content increase over the continental shelf is large and does not differ much. In summary, our above diagnostic of the freshwater storage capability reveals that the future Arctic atmosphere warming can significantly enhance the storage of freshwater under the forcing of increased freshwater supply by up to 40% in the Arctic main basin, 20% for the whole Arctic Ocean. And I showed you that earlier. Now they get into a discussion here. And the discussion gets kind of deep in the weeds. And someone reading this will kind of say, well, it's not clear what they're saying. It's a little bit confusing. They also seem to be contradicting themselves and so on. What they're trying to do is they're trying to think through the possible scenarios of what will happen to this fresh water based on the modeling, based on what the projected trends are for conditions in the region. And there is an important figure that I want to show you here. So what they did is they looked at the 2 and 3 times the riverine runoff based on the different models. Okay. And this is the freshwater storage capability as a percentage, right? So this is kind of a revisit. So we see here, as high as for the 370 model, about 45% above this reference historical one. So we see that it increases. But what's looking at the Ekman pumping? Now, the Ekman pumping is giving as velocity centimeters per day. Okay, so they got 1, 2, 3 times the runoff. Under the different warming scenarios, the Ekman pumping seems to be decreasing. The velocity, that is. As the freshwater capability increases, the pumping decreases. For example, let's look at 370 here. Okay, that's showing about 145%, about 45% above the reference. 370, look at the blue here. It shows that the centimeter per day, the pumping velocity has decreased by 1.1 centimeters per day. Look at 585, all right? That's about, 41, 42% above the baseline. And the pumping has decreased by about 1.35 centimeters per day. In other words, as the general trend here, as the freshwater capability increases, the Ekman pumping decreases. That's what that's showing. So what does that mean? We're talking about the center of the gyre, right? I showed you earlier how the vector fields will push in the water because we have the Beaufort gyre. So it's going to push the water. It's going to dome up in the middle. And when you have a convergence zone in the middle of a gyre, you have a downwelling at the center. This downwelling is decreasing. It's decreasing because it's fresh water. It's not as dense. So the sinking rate is going to decline. Just like what we see over in the North Atlantic, with all the freshwater input, the density current, the sinking is slowing. Well, if it's less dense, it's not going to sink as much. The pumping is going to decrease. That's what this is showing. This is a wonderful graphic. Increase the freshwater capability, the pumping in the center of the gyre is going to decrease. And that's what they're all talking about that here through the discussion and the conclusion. Now, as I said, in the discussion and conclusion, they kind of go all over the place a little bit there. So it may take, if for those of you who read the article, it may take you several reads to kind of get a handle on it. Let me see if I can sum it up for you. What they're basically looking at is, and then in the conclusion, they try to pull it all together. What they're saying is, okay, fresh water is accumulating in the Arctic. Okay? Precipitation is greater than evaporation. Sea ice is melting. Increase riverine input and contribution. These are all adding fresh water to the Arctic. What they're trying to figure out is what happens to that fresh water. If it stays in the Arctic Ocean, then you're going to have an extreme stratification. You're going to really have a pronounced stratification that may prohibit mixing across the halocline/pycnocline. That will have a deleterious impact on productivity in the water column. As I just showed you in that diagram, that fresh water accumulates, the pumping slows down, and you get this massive stratification. As I just said, you're not going to get that Ekman pumping. So now you're going to start putting this freshwater cap across the Arctic Ocean. And if certain circulation patterns, surface currents, persist or continue as they are, the Arctic boundary current and other lateral movements through there, it could be such that contains the fresh water. Just like the ice would be contained under certain conditions, and those certain conditions are, what does the Arctic dipole do? I did a video on the Arctic dipole explaining what that does. Basically, under one scenario, the location of the high and low pressure system are such that the flow is constrained within the Arctic Ocean so that the ice stays in place. But now if the ice melts, well, then the same flows could contain the fresh water. Under other situations, that ice can get pushed up the Fram Strait, which then leads to the other possible scenario. So the first scenario is the fresh water stays in the Arctic Ocean. The second scenario is the fresh water gets moved out of the Arctic Ocean and it gets sent into the North Atlantic. So if that happens, okay, so the gradient, the salinity gradient, will be lessened as opposed to being sharply defined. So you don't get a stronger stratification as you would if the fresh water simply accumulated. But if you move that fresh water out into the Atlantic, coupled with the melting of Greenland, you're really going to put a freshwater lens in the North Atlantic, really slowing down the overturned circulation, i.e., the thermohaline circulation, the vertical sinking, etc., the start of the conveyor belt, if you will. That's what's happening. So those are the two general scenarios we're trying to explain here, and you can go through that, but keep that in mind. So you're introducing a shitload of extra fresh water. It has to go somewhere. It either stays in the Arctic Ocean or moves out of the Arctic Ocean. And as I showed you with the advection from one basin to the other, this then allows the North Atlantic water to move in, just like was seen in the Barents Sea. Right? I did video about the Atlantification of the Barents Sea. Right? Done other videos about that. This is what's going on here. So, in their conclusion, our study indicates sea ice is an important control of the Arctic freshwater storage capability and upper ocean salinity. Sea ice decline enhances the ocean surface stress and Ekman transport. On the one hand, more freshwater is moved from the EB to the AB, tending to increase freshwater content in the AB. On the other hand, high salinity water of the Atlantic origin fills up the EB and even further spreads towards the AB, resulting in a freshwater decrease. Okay, that goes back to, does the freshwater stay or does the freshwater leave? Basically what that is. As a result, persistent sea ice decline, the freshwater increases and then decreases. Okay, that means evaporation and tends to decrease in EB. However, increasing river runoff modulates this counterbalance. Increasing river runoff delays the emergence of the decreasing trend in freshwater because you're melting snow, you're melting alpine glaciers, what have you. You have an increased precipitation in whole across the Arctic region, so that's going to increase the volume of the river, and the rivers flow into the Arctic Ocean, bring in that fresh water. So they go on to say that this is something that needs to get a better handle on, and further research is needed. So they suggest that the upper ocean stratification can be significantly strengthened by sea ice decline, along with the riverine input and the freshwater that accumulates, and the freshwater stays there, which can precondition winter deep convection. If you have this layer of fresh water on the top, you're not going to get that vertical mixing. You're not going to get that convection, or what we sometimes call ventilation. The possibility and timing of deep convection occurrence depend on the competing effects of sea ice decline, increases in Arctic freshwater supplies. Don't forget, I showed you some graphics from the work of Dr. Rebecca Woodgate, where she shows how the deep water convection in the Arctic Ocean is being affected by the heat as well as the freshwater input that's taking place. In her case, she's looking at it through the Bering Strait, but still, she's showing this convection being affected. So that would basically agree with what they're suggesting here. So hope you found this interesting. This is I've had people request that I cover some of the peer-reviewed papers, so I've been doing that. And as I said, I will leave the URL link so you can do a deep dive at your own leisure and at your own convenience. I'm giving the general background here. The take-home message is that the freshwater capability is increasing in the Arctic Ocean due to sea ice melting, increased precipitation, i.e. more precipitation and evaporation overall, as well as increased riverine discharges. What happens to that fresh water? How it affects the ocean? There are two major scenarios. fresh water overall stays in the Arctic Ocean due to the Arctic boundary current. Water is moved from the Eurasian side to the Amerasian side. That the fresh water then can affect Ekman pumping, i.e. the downwelling in the center of the Beaufort Gyre, for example. Or the other scenario is that through various transport and evacuation processes, the fresh water can move out through the Fram Strait. Therefore, any differences in salinity, the salinity gradient will not be as pronounced as if the fresh water stayed there. And if that fresh water, along with the melting from Greenland, accumulates in the North Atlantic, well, we know what the implications of those are. So this is going to be something to look to. So what happens here? Freshwater stay in the Arctic Ocean, we get a sharp salinity gradient, so you may not be able to mix the nutrients through, which means that the vertical mixing convection is depressed. Or if it is pumped out here, then perhaps you could get some mixing through the halocline. The salinity gradient would not be as sharp, and then you can get some of the deeper mixing. This all remains to be seen. But those are the two major scenarios that are coming out of this, what I consider to be a very important paper. So there you have it. Hopefully I didn't confuse the crap out of you guys. But thank you for your time, and we'll talk soon. Hello, folks. This is Jim here with Science Talk, asking you to please subscribe to my channel and to inform others of my channel and of the work that I do. Please share to social media platforms that you use. Also, as a reminder, don't forget to click the bell so that you know when I load up more videos. Finally, I ask that you support the work that I do by becoming a patron at patreon.com. Details in the description box below. Thank you for your support.